Let's find the distance between the point A, which is 2, 2, 3, and the line L, which passes through the point 4, 4, 4, and which also has direction vector 3, 2, 1. Well, let's start by giving a name to this point 4, 4, 4. Let's call it B. And let's give a name to our direction vector also. I think D would be a natural name there. So let's say the vector D is the vector 3, 2, 1. That way we can draw a representative sketch. So what we've got is this line L, which contains our point B and which travels parallel to this direction vector here. So let's say there's D. I'm just going to draw a dotted line here to represent our line L. And we've got this point A here, which we can check does not lie on this line L. So let's say, just for the sake of a representative sketch, let's say A is over here. It doesn't really matter where you position A, you will come up with the same answer for the distance at the end of the problem. It's just a representative sketch. So you could draw A over here if you like, or down here if you like. It will not affect your final answer. Now what we want to find is the distance, meaning the perpendicular distance between the point A and the line L. So if we drop a perpendicular down to L, that might look something like this. We are looking for this distance here. So I'm going to put a question mark there. That is what we're trying to find. All right, so let's draw our point B, our direction vector D, and our point A, which we've said is over here. And let's identify the vector AB in our sketch. Okay, so that vector is traveling from A to B. Now, if we were to project this vector AB onto D, we would end up with this little vector here, which looks like that. So I'm going to label this out of the way here. Let's say that's the projection onto D of AB. And we've also got this vector here which travels straight down perpendicular to L. This vector here, which we've just drawn, is AB minus the projection onto D of AB. So just as a double check that this is correct, let's confirm that if we add this vector here to this vector here, we should in fact be creating the vector AB. So yes, if we add the projection here, this projection to AB minus the projection, we do in fact end up with AB. So that way we know that we've got all our signs correct here. All right, now to answer the problem, what we're trying to find is this perpendicular distance here down to the line. The way we're going to find that is just by taking the length of this vector here, this AB minus the projection onto D of AB. So let's write up here the distance that we are ultimately trying to find will be the length or the norm of AB minus the projection onto D of AB. So we'll do some intermediate calculations here to come up with our answer. Let's start by calculating the vector AB. So algebraically, we're taking the point B, we're going B minus A, gives us the vector 2, 2, 1. We then want to project onto D, and what we're projecting onto D is that vector AB. So according to our projection formula, we're going to take the dot product of these two vectors, AB dot D, and everything else is about that vector that we're projecting onto. So we'll be dividing by the square, the norm squared of D, and that will be in the direction of D. So calculating this dot product, AB dot D, is going to give us 3 times 2 plus 2 times 2 plus 1 times 1. All right, so that's 11. Divided by the norm squared of D, that's 14 in the direction D. All right, so we've got 11/14 times that vector 3, 2, 1. Now we need to calculate AB minus the projection onto D of AB. Okay, looking ahead at our calculation here, since this projection involves this fraction here, this 11 over 14, I think I'm going to write everything over 14. And let's call that vector AB 14 over 14 times the vector 2, 2, 1. Just makes the algebra a little bit easier. Rather than just writing 2, 2, 1, I'm going to write 14 over 14 times 2, 2, 1 so that we can more easily subtract off this 11/14 times the vector 3, 2, 1. Okay, now you could come up with your answer in one step here. If you want to be a little bit more careful with the algebra, you might do something like, say, 1/14 times the vector 28, 28, 14, just to make absolutely sure that that 14 gets multiplied through. Similarly, you could go minus and do something like 1/14 times the vector 33, 22, 11. I tend to make these kind of algebra mistakes if I rush here, so I'm just putting in this step. It's optional here. You could probably jump down to your final answer here in one step if you're feeling comfortable with it. We're going to have 1/14 times the following vector. We'll have to go 28 minus 33 gives us -5, 28 minus 22 gives us 6, and 14 minus 11 gives us 3. All right, so at this point we have found the vector AB minus the projection onto D of AB. The very last thing we'll need to do is calculate the norm of this vector, and then we will have our distance. So just copying from the previous screen, we said that the distance is the norm of the vector AB minus the projection onto D of AB. And we found on the following screen as well what that vector specifically looks like. So it was the vector -5/14, 6/14, and 3/14. And just for the sake of calculating the length here, I've multiplied that 1 over 14 through. So according to our formula for distance, we're going to take the square root of the following expression. We're going to go through and square each of the components. So we'll watch our signs here. The first component squared is going to give us 25 over 196. Okay, and we're going to add up this sum here, sum of the squares. So next component gives us 36 over 196. Last component 9 over 196. So under the square root here, we've got a total of 70 over 196. That looks good. And then we can apply the square root to the top and the bottom. So that's root 70 over, well, we know root 196 is going to be 14. So final answer to the problem, the distance we're looking for, root 70 over 14.